Hi everyone, welcome to the second lesson for topic 3.3 Graph and Networks. So in the previous lesson, we have covered the part which we discussed about different elements in a graph. So by now, I hope that you are familiar with all the terminology or the new vocabulary that we mentioned in the previous lesson. For example, what is that meant by edge, vertex, face, multiple edges, loops, and so on. Okay, then by looking at the different composition of edges and vertices, we also come to know the different types of the graph as well. So this is what we have covered in our first lesson. So for today's lesson, we are going to look at the other type of graph, which is known as planar graph. So two learning outcomes for the day. The first one is you will understand what is the meaning of a planar graph, what is the definition of a planar graph. Second thing is when we talk about a planar graph, there will be one identity that you will need to learn, which is known as the Euler's formula. So you'll be able to understand how is this formula works, and you'll try to use it to solve the problems. Okay, so basically that are the two things. So remember, first one, what is that meant by planar graph? Second thing, how to apply Euler's formula. Okay, so that's basically the idea. So let's start with the first part. Alright, so let's start with what is that meant by a planar graph. So a planar graph is a graph that can be drawn in a plane. So that's the first thing. Okay, a plane meaning like a 2D plane, for example, a Cartesian plane where you plot your graph. For example, when the table surface that you are currently writing on, so that's like a 2D surface, right? Yeah, so that's a plane. So yeah, when you try to look at the word here, planar graph, so you can relate it to the word of plane. So a planar graph can always be drawn so that no two edges cross, or sometimes you can say overlapping or intersecting. Okay, let's try to do a very simple example here. So when we try to draw like a graph, okay, so this is a simple graph. So with four edges and four vertices, right? Yeah. So this is a planar graph. So as you can see, I draw all the vertex and all the edges here on a plane. And then, yeah, it's not like a 3D shape. And then there's none of the edges crossing over each other. Okay, so even I try to draw something like this, okay, and if let's say I continue on, yeah, so as long as the shape that the graph come out to be on a plane, and then there's none of the edges crossing over each other, so this is called as a planar graph. So a graph may appear as non-planar but can be redrawn without any of the edges intersecting. Okay, so we try to look at this simple example here. So you can see that this is a complete graph which we known as K4, if you remember from the previous lecture. So you can see that all of the all of the vertices here, they are adjacent to each other. They are directly connected to each other. So for example, when you try to look at A, so it's reachable with you can reach another vertex by only one edge, right? So C to D to E to B and so on. So this is called as a complete graph. So by looking at this graph here, so it appears as a non-planar graph. Why is that so? Because AD and BC, they intersect each other. So I want you to try to imagine this picture as if, for example, you have four plugs here. So all the edges are the wires that you can see. So when you have this thing, right, so you can imagine that the edge of AD is like one wire connecting A to D. Then the edge from B to C is like another wire connecting these two plugs. So that's why you have like two wires. So they might, obviously they will be overlapping each other. Am I right? So you can imagine like BC is at the bottom, then AD is like at the top. So they are like overlapping each other like these two wire. Okay, so that's why this is appear as non-planar. But what we can try to do is we can try to redraw the graph. So how can we do that? So let's try to draw the part where the graph didn't overlapping each other first. For example, we have the ABCD part. Okay, I'm going to draw a smaller one because I want to show you like different way that you can draw it. Okay, so A, B, C, D. So now these are the two edges that crossing over each other. Am I right? So that's why we can choose one of it and just leave it in the middle. For example, BC stay in the middle. Okay, so what happened here is we need to find an alternative to draw the edge for AD. Am I right? We cannot draw it in the middle because if you draw it in the middle, then it's going to be the same thing lah. The edge will intersecting again. Okay, so now what we can try to do is we try to place the edge for AD in another position. So by using the illustration just now when we talk about the wire thing, so now these two wires overlapping with each other. So what you can try to do so that the wire is not overlapping each other anymore. So for the wire for AD, you will try to take it up, then you just try to remove it. It's not remove, sorry. You just try to pull it outside so that you can place it outside that it didn't overlap with BC anymore. You get what I mean, right? So we try to pull this wire, then after that, we try to place it outside. So you can see that there's still there's still one edge connecting the vertex A and D together. But now this graph has no edges intersecting with each other anymore. So this graph, after you redraw, then it appears as a planar graph. Okay, so again, let's go back to the definition, right? The definition says that a planar graph is a graph that can be drawn in a plane. So that's why this is known as a planar graph as well, but it's just appear as non-planar. Then what we need to do is we need to redraw it so that it can be planar. But remember that not every graph you can redraw it to be a non-planar. Later we'll be looking at like one of the example. Okay, so then you might have a question, is this the only options that I can draw? No, so you can draw it in different way. For example, if let's try to draw a similar one. Okay, so if let's say A, B, C, A, B, C, and also D. Okay, so instead of pulling AD outside, then what you try to do is you want AD to stay inside. So what you need to do is you still have another edge to draw, right? So which is the edge for BC. So what you can try to do, so you draw another edge connecting C and B together. Okay, so they are just the same thing. So what is more important is you must make sure that the number of vertices, the number of edges, and the way that they connect with each other must be the same after you redraw the graph. So for example, you can see that whether the vertices are adjacent to each other or not, whether this vertex is adjacent to each other or not, it's still the same after you redraw it. Okay, so let me try to give you another example which doesn't look like this shape anymore. Okay, but looking at this, then it's still quite similar. Another thing that you can try to see is, okay, I try to take out the vertex of A. So you can see that the vertex of A actually actually adjacent to all the other vertex B, C, and D. So what I try to do here, maybe A in the middle. Okay, then I try to redraw the whole thing. So B is here, and then C is here, and then D is here. Let me try to replace okay, so D is here. And then my A is in the middle, right? Okay, so you can see A is adjacent to B, C, and D. Then we know that it's a complete graph, right? So B is adjacent to A, C, D as well. So can I do that? B is adjacent to A, C, and also D. Then the same thing, D should be adjacent to every other vertex as well, right? So D, let me try to draw it properly. So D, you can draw it connecting to B and connecting to C. So now when you try to look at C, is it adjacent to every other vertex? Yes, so A, B, and D. So that's why this is actually a planar graph as well. Okay, so as long as the idea is you have the same number of vertex, same number of edges, and the edges that connecting the vertex are still the same. Okay, so now you can see that this graph is drawn on the plane and there's none of the edge intersecting or overlapping each other. Okay, so this is how we want to deal with it. Okay, so a simple notes before we move on to the example, right, is what I mentioned in the previous lecture, which I mentioned that stating a vertex is very important in a graph. So let's try to look at this simple graph here. So you can see that these two graphs are pretty similar, am I right? So the only difference is whether you have a vertex in the middle or not. So stating a vertex is very important because whether or not you have a vertices in the middle, it actually brings different meaning to this picture. Okay, for example, ABCD is what we have in the first place here, right? So ABCD appear as a non-planar graph because what you can see here is that the graph for BC and AD, they overlapping each other. But then in this case, right, EFGHI is actually appear as a planar graph because you can see that if let's say you have a vertex in the middle, which means you imagine if you have another plot in the middle, right, then you are connecting the wire from E to I, wire from E to F, E to G, and E to H. So that's why there's actually no overlapping, no crossing over for the wire. It's just everything connecting to the middle. Am I right? Then the second difference is that when we try to look at the first graph here, this is a complete graph like what we mentioned just now is a K4 graph. So all the vertex, they are adjacent to each other. But when you try to look at the graph for EFGHI, it's not a complete graph. So why is that so? Because you can see that the vertex F is not adjacent to the vertex H. So you see, right? Now, when you want to reach H from F, you must pass through E. Am I right? So you cannot directly connect to H by using only one H. So which means F and H is no longer adjacent to each other. The same thing goes for G and I, because you can see that G and I is not directly connected anymore as well. So that's why it's important for you to understand whether or not you have a vertex in the middle, they means different thing. So understand it as if this is like two wire overlapping each other. This is like you have different four wire connecting with each other in the middle. So when you try to look at this type of graph, right, the thing that please make sure when you try to redraw your planar graph, do not add one vertex in the middle because that will bring different meaning to the graph. So that's why maybe you have an idea where why not if let's say this is not a planar, then I just add in one of the vertex, then this become a planar. But like what I said just now, so if let's say now you are planning on something like building electric cable, so these are the four poles that you have. So you can't actually just add anything as you want, right? So the connection must be still the same, but it's just that you can try to draw it in another way. Okay, so now let's move on to the example and we try to redraw some of the graph. All right, question one, identify if the graph is a planar graph. So I think it's good for us to revisit the definition again. So the planar graph is a graph that can be drawn in a plane without any edges crossing over each other. So remember, the idea is can be drawn. So I hope that you don't look at A, B, C, D, then you tell me that all of them are not planar because you can see that they are edges crossing over each other. So the idea is as long as you can draw so that it can be an obvious planar graph, so it is still considered a planar graph. It doesn't it doesn't mean that when you try to look at the graph then you have crossing, then you tell me not a planar graph. Okay, so it's that you will need to redraw the thing, then after that you identify whether you can draw it or not. Okay, so let's start with A. So same thing, let's try to start with the part without any edges crossing over each other first, then I guess that will be easier. So in this case, you can see that we have ZW and also YX. Okay, so here ZW, then maybe we have here, we have Y and X. Okay, so these are the edges without crossing over each other. So you have WY and ZX are the edges crossing over. So same thing, you can pick either one. So in this case, let's try to do this. Okay, so if let's say we try to pick Z and X, then which means that we will need to pull up the wire here. So we'll need to, place this edge of WY in another way. So which means in this case, then you just try to connect it the other way. Okay, so let me try to say it again. Make sure that you try to label your vertex well. Okay, so you can see that you still have 4 vertex here, which is W, Z, Y, X. So make sure that 1, 2, 3, 4, 4H, 1, 2, 3, 4, and they are connecting to the right position. Okay, so if you don't have to do like this, then the same thing you can try to draw the other way around as well. So for example, if let's say W, Z, so X and Y. Okay, so if let's say you try to connect these two, then if you try to connect here, okay, then which means the other thing is you need to connect Z and X together lor, then you just draw outside. Okay, so yeah, as long as it become a obvious planar graph, then after that you still have the same vertex and the edge connecting the same thing. Okay, so let's move on to B. So yes, it's a planar graph lah, so you just write down yes. Okay, B. So let's see the same thing here. So the two edges crossing over each other is these two. So we can try to draw the rest first. So we can try to have M, N, K, L, J. Okay, so yeah. So now let's try to see how can we move the edge that crossing over each other to the other place. So same thing, depends on you. I mean whether you want to connect M and K together or you want to connect J and N together. So if you choose to connect J and N together, then the thing that you need to draw is M and K here. Okay, so yeah, that's the idea. So the other thing that you can try to draw is if you are drawing MK, then yeah, maybe I'll draw the other one as well. Yeah, I'm just going to show you that, I mean, there are there are different possibility that you can try to do that. So that's like not one answer kind of thing. But the idea is you must make sure that the thing that you draw has the same meaning with the previous one. So this is the J. So if you want to draw it like this, then which means that JK here, okay, then you will have another JN that you need to draw lor. So then it will be outside here. Okay, so this is yes also. All right, so move on to C. So yeah, starting, this might be a little bit hard. Okay, I recommend you please use your pencil first because you are going to erase it. So I'm just going to show you an example here, or you use the other color of pen lah. Yeah, just to tell you that, I mean, in this case, this is a quite difficult one that you want to draw. Okay, so you can see, right, the thing that they overlapping each other is quite a lot. So you can see these two, these two, these two, these two, and these two. So there are like eventually 5 places that you will need to remove, or you need to reposition them again. So imagine if let's say we try to keep our AC here. Okay, or let's try to just draw with the original graph here. So imagine what we try to do. We remove AD, BD, draw it outside. Is that okay? So now imagine this line is no longer here. So I already moved BD outside. Okay, then after that I still have crossing over here, right? So that's why I remove this outside as well. BE. Okay, then the same thing. So now BE is removed outside already. Okay, so I erase that. Okay, is there any more overlapping? Yes, right? This part. So you see, this is the problem now. So either are you going to draw it like this? It's going to cross again here. Or are you going to bring your CE outside? Then it's the same thing. You are going to cross over with the blue line here. So that's why you realize that it seems to have like none of the way that can actually help you to draw that. So how you can try to do it? So the thing that we normally use is you try to reposition the whole thing. So I mean you need to move the vertices as well. So it's easier in this way that you can understand that this is like a thing, if you know how to draw a star, right, then everything can be drawn in one, in one line. So you can it's a continuous process to draw a line. So that's why you can imagine that what we can try to do is we just place it outside. So A connect to C, right? C connect to E, and then E connect A, C, E, B, D. So B and D. So you can imagine that eventually everything can just connect it with a pentagon. Let's try to check out. So you see how many edges you have here. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Am I right? Vertex 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So are the lines connecting all the correct vertex? So AC, so you have AC. CE, so you have CE. EB, then you have EB. DE, DB, then you have DB. Then AD, you have AD as well. So everything is the same. So that's why this is a planar graph. So it's a yes. But it's just a little bit harder because eventually you need to reposition the whole thing. Okay, so this is part C. Okay, so now let's move on for D. So yeah, I can straight away tell you that this is one of the example that you can't redraw it as a planar graph. So sorry, let me try to rephrase my word. It is not a planar graph, so no matter how you draw it, it cannot be appear as a planar graph. Okay, so why is that? So you see, this is actually a complete bipartite graph. So you can see that there's like one group 1, 2, 3, another group 1, 2, 3, and all of the vertex in one group, they are adjacent to the other 3 vertex in another group. So this is a complete bipartite graph from what we learned previously. Okay, so now let's see how are we going to redraw it. So you can imagine that we will need to do some repositioning like what we did in part C as well. So what I'll try to do here is for an easier explanation, I'll try to use different color. So this is like one group, the yellow color one. Then I have the other group, which is like the blue color one. Okay, so imagine that you can bipartite graph only connect the vertex from different group to only connect the vertices from different group, right? There's none of the edges that will connect the vertex from the same group. So that's why the easier way to do that is like how we draw the star just now. So we are trying to place it in such a shape that blue, yellow, and blue. Let me try to finish all the blue. Blue, okay? Blue, yellow, blue, and then yellow, blue here. Then we put another yellow here. Okay? I hope that you agree with me. So this is like how you try to draw it. So that's why you can have everything here already. So let's try to draw it. Okay, so because it's a complete bipartite graph, right? So all the blue color must be adjacent to all the yellow color. So 1, 2. So the same thing, the blue color adjacent to the yellow color, blue color adjacent to the yellow color. Okay, so now the thing is not complete yet. Why is that so? Because you need to make sure that all of your vertex of one color connect to different color. So the blue color should be adjacent to all the other, right? So that's why we try to connect here. Okay, so everything still looks good, right? It's still a planar graph. It still appear as a planar graph. Okay, but now when we continue, so this blue vertex here has to connect with the yellow vertex here as well. So you cannot cross in the middle anymore because it will make your graph crossing over each other. So you need to cross outside. Okay, so now then, yeah, this still looks fine. But when you move on, right, you'll realize that one of the vertex here is not adjacent to this yellow color yet. So what do you need to do? You need to draw another line. But the problem here is that you wouldn't able to draw another line anymore because no matter you want to draw it here or no matter you want to draw it here, by all means, you are going to cross with the other line that you draw, which is just now the line here. So you can try and see, you can use different approach to try to redraw this, but you'll never be able to draw a planar graph out of that. So that's why this is actually not a planar graph. Okay, so yeah, that's the idea of it. So normally for planar graph, it's easier for us to see whether the graph can be drawn as a planar or not. So if let's say it's a yes, right, then it will be easier. If it's no, then you'll need to try out different approach and see is it at the end you really can't draw it? Yeah, so that's the idea. So which mean no matter how you replace everything, right, then it still be intersection like what we did here, then you know that it's going to be a non-planar graph. So you can always try this out. Okay, so now let's move on to the identity, which is known as the Euler's rule. Okay, Euler's rule or sometimes Euler's formula or even Euler's identity, they are just the same thing. Okay, so they state that for a connected planar graph, so remember this rule only applies for connected planar graph. So which means if let's say you have a planar graph like this, then Euler's rule then is a yes. So if let's say you have a planar graph, for example, okay, like this, yeah. Okay, so this is also a planar graph, am I right? Because you are drawing it on a plane, then there's none of the edges intersecting with each other as well. But this is not a connected graph because you can see these two parts, they are disconnected from each other. You cannot reach the vertex here if let's say you start with a vertex here, and you cannot reach the vertex here if you start from a vertex here, am I right? So this is not a connected graph, so you cannot use Euler's rule here. Okay, so for a connected planar graph, Euler's rule states that V plus F minus E is equal to 2. So this is a formula that given in your learning outcome as well. So what is that meant by V is the number of vertices. So start with V, right? So vertices V. So E meaning is a number of edges. Then F is the number of faces. In another words, Euler's rule tells us that for a connected planar graph, whenever you use your number of vertices plus your number of faces minus your number of edges, it will always give you 2. Okay, so let's try to go through the 4 example that we did just now and try out whether it's correct or not. Okay, so remember this are V plus F minus E equals to 2. Alright, so let's try to see whether it's true or not by using the previous example that we did. Okay, so we have V plus F minus E is equals to 2. Okay, so how many vertex that you have? 1, 2, 3, 4, right? So 4. How many face that you have here? 1 inside and another one outside, right? Remember, outside region is considered as 1 face, so 2. So how many edges? 1, 2, 3, 4. So minus 4. So what do you get? You get 2. So yes, right? So next one, let's check. So how many vertex you have? 1, 2, 3, 4, 5. So that's 5. Then after that, how many faces that you have? 1, 2, 3, 4. Outside, right? So 4. Then how many edge you have? 1, 2, 3, 4, 5, 6, 7. So minus 7. What do you get? You get 2. So yes. Okay, then we move on. For this one, you have how many vertex? 1, 2, 3, 4, 5. So 5. Okay, then face, 1 inside, another one outside. Then how many edges? 1, 2, 3, 4, 5. So 5. 5 plus 2 minus 5, you get 2 as well. So for this one, because it's not a planar graph, so we know that Euler's rule doesn't apply. Okay, so I hope that you can see it's pretty interesting, right? Yeah, so you can try to check out more. I mean, in your textbook, right? Yeah, the one that you have a lot of questions that you need to come up with the vertex, face, and also the edges. Yeah, you can try it out. So everything will applies to Euler's rule as long as it's a connected planar graph. Okay, so we'll look at 2 more examples to see how do you actually answer the question about Euler's rule. Oh yeah, before we move on to the example, I think maybe you might have this question. So if let's say you have a planar graph, then after you redraw it, right, then when you check by using the Euler's rule, and you realize that when you use your V plus F minus E, you doesn't get 2, is that mean that your graph is wrong? So the answer is yes, it means that your graph is wrong. So which means that this is a 100% rule. As long as it's a connected planar graph, it should satisfy Euler's rule, which states that V plus F minus E is equals to 2. So which means if let's say you use your vertex plus your face and minus your edge and it gives you 5, right, then you know that your planar graph got something wrong there already. Okay, So that's the idea. So which means by using this rule, right, you also will be able to guess like how many edges you have. For example, if let's say I give you an idea where there is a planar graph which the number of vertex is 5 and then the number of faces is 3. So can you tell me how many edges you should have? Yeah, so it should be 6 because 5 plus 3 needs to minus 6, then only you get 2. So that's the idea. So this is like a rule identity kind of thing. So all the connected planar graph should satisfy or should be able to fit into this rule. Okay, so the same thing if you are given V and E, then also you can solve for F as well. If you are given F and E, then you will be able to solve for V as well. So that's the idea. Okay, so let's look at another two example. Okay, number two, show that the following graph is planar by redrawing the graph so that no edge intersects. Okay, then after that, B, using Euler's formula. Oh yeah, this one. Remember Euler's formula didn't apply if let's say you didn't redraw it. So for example, you can see 1, 2, 3, 4, 5, 5 vertex, right? Then after that, plus your F. So 1, 2, 3, 4, 5, 5 outside. Then minus off your H. 1, 2, 3, 4, 5, 6. So 6. So you can see 10 minus 6, you are getting 4. So I mean, this is also called as a planar graph because you can redraw it and it becomes like no edge intersecting each other, right? But before you redraw it, then you cannot use Euler's rule. Euler's rule only apply for the graph that appear as a planar graph. Okay, it's not before your redrawing, it's after your redrawing. Okay, so let's try to redraw our graph first. So I guess this is not too hard. If you want, then you can try to pause the video then and try to draw the graph by yourself. Then after that, you check your answer. Okay, because yeah, I mean, it's quite obvious that these three edges are the one that intersecting with each other. So you actually have two alternatives lah. The first one is you bring QS outside. So which if you were to draw it, then it will become like this. So you have a triangle here. Okay, then the other thing stays the same. Okay, so P, T, R, Q, and S. Okay, so the thing that intersecting, crossing over is like the QS, right? So we just bring it outside. Okay, so remember your vertex. Okay, so same thing, you can check and see is it 5 vertex here. So 1, 2, 3, 4, 5, 6, 6 edges. 1, 2, 3, 4, 5, 6. Okay, then after that, you have all the same connection in the graph, then you know that's wrong. Oh, sorry, you know that's right. Okay, then the other thing that you can try to draw is if you want to move PR and TR outside, so that also works. So in this case, then you might need to draw a trapezium. Okay, then after that, yeah, this thing you draw it outside. Then let's try to plot this first. Okay, so which means in this case, R is still here, but then you cannot cross over here anymore, right? Then we just draw it outside. Oh, sorry. Okay, then I'll just draw outside. Make sure please use your ruler in your handout. Yeah, so yeah, draw it outside as well. Okay, so this is like the graph that you have. Sorry, it's a bit okay, but yeah, that's the idea. So P, T, S, and Q. Okay, so now B, the question wants us to use Euler's formula and prove that whether it's a planar or not. So after we draw the graph, so we can try to check. Okay, so again, in this case, I'll try to write everything properly so you know how should you write down your Euler's formula properly. So please make sure that you follow the idea because, okay, make sure that you do not straight away write V plus F minus E equals to 2 in your exam because I know that that's your Euler's formula. But at the end, what you need to do is you need to show that this thing is equals to 2. So that's why it will be good that you try to state everything that you try to do here. So for example, we know that we need to get the number of vertex, right? So that's why start with stating everything first. So V is equal to number of vertex 1, 2, 3, 4, 5. So no matter which one you are drawing, it's still 5, right? Then after that, faces. So you see 1, 2, 3 outside. Same thing, 1, 2, 3 outside. So no matter which graph that you are drawing, it still give you three faces. Then how many edges that you have? Just now we count is six. 1, 2, 3, 4, 5, 6. Same thing. 1, 2, 3, 4, 5, 6. So E is 6. So after you state everything, then only you go and write down FV plus F minus E is equal to 5 plus 3 minus 6. Then you write equals to 2. Then only you show it. Okay, so that's how you should write it in exact. So now example 3. Okay, example 3 show that the following graph is planar by redrawing the graph, then use Euler's formulas to check that as well. Okay, so for this picture, it looks a bit complicated, but yeah, don't worry about that. You just look at it, then you should be able to do that. So first thing, identify first where's the intersection point, and you decide which is the edge that you want to move it away. So for example, you can see that this is a place that they intersect, right? So these are three places. Okay, then the thing that it might make our life easier is that try to move, make the least change as you can. Because, okay, for example, how do I normally decide like which is the line that I want to move is that you can imagine, right? These are the intersection, these are the points that they crossing over each other. So you can actually pick you want to bring BD outside, you want to bring BG outside, or you want to bring AC outside, am I right? Because these are the three lines that involve. Then you can ask yourself the question is there anything that I can do? I can only move one, then I settle the rest of the problem. So by using this idea, then I'll be able to know that it's easier for me to bring AC outside. Because once I bring AC outside, then BD and BG now is becoming planar already. Like BD and BG, they are not intersecting with each other before, right? But then you imagine if let's say I bring BG outside, then it's still going to be an intersecting point for AC and BD. So that doesn't help a lot. So that's why I might as well choose AC outside. Then the same thing, the intersection point here. So you can see that once I move AF outside, then I'll settle everything here. Am I right? So this line isn't here anymore. Then the other thing is here. So it's the same idea as well. So you can see that CF is the line that crossing over BG, DG, and EG. So that's why it will be much easier that I just bring it outside. So this will just give me a planar graph after I move these three lines away. Okay, so now let's try to redraw the diagram. Okay, so in this case, then what you can try to do is you can try to do the triangle in the middle maybe. So this thing, sorry for that, it's a bit difficult without the, okay, yeah, so this is what you have in the middle. Yeah, so because we are moving the line only, right, so that's why the vertex is still the same, so you can still try to draw the exactly same thing. Okay, so just now you can see that this one we doesn't move it, so it still stays, this one still stays. Okay, so the one that we move it is the line, the edge that connect F and C together. So F and C together will be drawn outside. Okay, then after that, the other one is A and C together. So A and C outside. Another A and C outside as well. Okay, so this is what you have. Sorry, it's a bit ugly on my side. I hope that I do a better one by using a ruler. Okay, so G is here, then C, and then F. Okay, so you see, yeah, please remember to check again your vertex lah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, okay, that's right. Then the vertex all the same lah, A, B, C, D, E until G. So yeah. Okay, so after we have this, then now let's move on for Euler's rule. So same thing as well. Let's state everything first. So how many vertex we have? A, B, 1, 2, 3, 4, 5, 6, 7. So 7. How many faces we have? 1, 2, 3, 4, 5 outside. So 5. So how many edge that we have? Just now we count already is 10, right? Okay, then when we use V plus E, F minus E, So 7 plus 5 minus 10, then we have 2. So that's why you are shown. Okay, yeah, so that's the idea. Okay, so yeah, that's pretty much of the important part. Then we are just going to talk about one last application for planar graph, which is how do we convert the 3D shape into a 2D shape. Okay, so let's move on to the large page of the handout, or last page of the handout. Okay, last part. So an application of planar graph is to convert a three-dimensional solid into a two-dimensional projection of the shape. Okay, so let's try to look at one example, then you'll understand what I mean here. So this cube can be redrawn as a planar graph. So how do we do that? So for an easier way, let's try to look at it like this. So you can see that we have one face in the front, am I right? So which is A, B, C, D here. So let's try to do that first. So A, B, C, D as a square. Okay, that's right? Then after that we have A, this is B, C, and then D. So it represents the face in the front here. Okay, so now when we try to look at this cube, right, then you can see that A is adjacent to E, B, and also D. So now A is adjacent to B and D already. Then now what we can try to do is we try to extend the line. So we try to draw a plot E here. Is that okay? So now A is connected, or A is adjacent to E, D, and B already. Am I right? So E, D, and B. So the same thing, now let's look at D. So D is adjacent to the vertex of A, F, and C. So you have A, C. So let's try to extend an F here. And you realize that F and E, they are adjacent to each other. Am I right? So same thing, when we try to extend it, then you can realize that no matter where you want to start, so for example, I want to look at F. F is adjacent to E, D, and G. So E, D, then I'll draw another G here. So G is adjacent to F, C, and H. So that's why I should have another H here. And also G is adjacent to C. Am I right? Then after that, I'll try to just draw them together and check. Okay, so this is what I get a planar graph for a cube. So let's try to see is there every criteria that we have fulfills or not. So when we try to look at this 3D cube, how many faces that you have? So we have the face at the top, we have the face at the side, 1, 2, 3, at the back, at the front, and at the bottom. Am I right? So you have 1, 2, 3, 4, front and back, 5, 6. So that's why you have 6. How many vertex that you have for the cube? 1, 2, 3, 4, 5, 6, 7, 8. So 8 vertices. So how many edges? Edges is like the place where you connect the vertex together. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12. So same thing, let's try to look at the planar graph that we try to draw here. How many faces that you have? 1, 2, 3, 4, 5. Don't forget outside as 1. So that's why you also have 6 faces. Then how many vertex? A, B, C, D, E until H, right? 1, 2, 3, 4, 5, 6, 7, 8. So same things, 8 vertices. How many edges that we have? So you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's why 12 edges. And you can see that all the edges still connecting the same vertices. So for example, when you try to check H, then H is still adjacent to EBG. So EBG. Then whenever which one you try to check, it's adjacent to the other three. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it's all the same. So that's why you can see that a 3D solid can be redrawn as a planar graph. So all the faces, vertices, edges, all the composition still stays the same. It's just that now this graph is drawn in a plane and there's no edges that intersecting each other. Okay, so that's the idea. That's one of the special application for a planar graph. Okay, So before we try to end here, yeah, so you can see the edges still connecting the same vertices, so it's just been drawn in a 2D form. Okay, so let's try to draw a very last one before we end the lesson here. So this is a three-dimensional triangular prism. So same thing, let's try to imagine how should you draw the planar graph. Okay, so let's try to draw an easier one. Same thing, let's try to draw from the front here. So you have a triangle of ABC, right? So that's why let's start with that. So A, B, C. Okay, A here, B here, and C here. Oops, I might need to move my alphabet a bit. So, yeah, sorry. Okay, then after that, I know that B is adjacent to D. A is adjacent to D, B is adjacent to E, and C is adjacent to F at the back, right? So that's why what I can try to do is I just extend the line. Okay, it doesn't has to be in this case. If you want to do like in another way also can, but just make sure that you cannot have edges that intersecting with each other. So that's the idea. Okay, so let's try to do it again with a better. Okay, so A is adjacent to D, right? Then B is adjacent to E, and then C is adjacent to F. And you must make sure that D, E, F, they are adjacent to each other as well. So at the end, you have something like this. Okay, is that fine? I hope that you can see the idea. Yeah, so let's try to check. Yeah, so A is adjacent to B, C, and D. So B, C, and D. Then E is adjacent to D, F, and B. So you look at E, then you can see D, F, and D. So that's right. Okay, so you can check out for everything as well. So make sure that you have the same edge, same vertex, the same face. So the face that you have, you can see the slanted one, you have 1, then 2 here, right? 1, 2, 3, 4, and 5. So 1, 2, 3, 4, 5, and that's correct. Then the same thing here, you can try to check 1, 2, 3, 4, 5, 6. So 6 vertices. Then after that, the last one, the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's correct. Okay. So do you have another alternative other than that? Yes, you can. You can draw it from the top as well. So you can try to draw AD. Okay, so you can have AD like this. Yeah, then you know that for DE is going to be like triangle, right? So that's why you can draw it like this also. Yeah, so the idea is as long as you can see the shape. Okay, so you can see that AD is at the top here. So A is adjacent to BC, so this is the BC. So B is adjacent to E at the back here, right? Then C is adjacent to the F at the back here. So you can see DEF is like the triangle at the back. BAC is like the triangle at the back. Then you are looking at from the top. So this is like the tree. Okay, so same thing, you can try to check all the adjacency should be the same. So like which edges connecting with which one, so it should be the same. Then the same thing that you have 6 vertex here, then 9 edges, and also 1, 2, 3, 4, 5, 5 face. Okay, then the same thing, the other thing that maybe you can try to draw one more. So let me try to see. Oh, we can try to do AD also, but in another way. So if you are drawing it like this also can. So AD, then you might have your DF at the back. Okay, then maybe when you are drawing it, then okay, so let me try to draw it first. So this is A, D, then E and F. Okay, so when you are trying to draw it, maybe you accidentally draw it like this. Yeah, it can be accepted as well. So A, this is B, this is C. But now you realize that you have one problem is you lack out with one edges, which is from B to C. Am I right? Then you realize that you cannot draw in the middle here because it will cross with AD. Then what you can try to do, just draw it outside. Yeah, so this is considered as a planar graph as well. So you can try to check the face, the edges that connecting to the vertex, they are all the same also. Okay. So the last thing before we end the lesson here, let's try to check the last one. So you see how many vertex that we have here? 6. So how many face? So no matter which one you are drawing, you realize that you always have 4 faces. You can just try to draw it out with different possibility lah. So you will still get the exact same thing also. So each that we mentioned just now, we have, is it 9? One, sorry. Just now you say it's 9, right? Then is it wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's 9. Anything wrong? Oh, sorry. The face. Yeah. Okay, 1, 2, 3, 4, 5 outside. Sorry, my mistake. Okay, so V plus F minus E. So you have 6 plus 5 minus 9, so which give you 2 as well. Okay, so that's why it's shown. So same thing goes for the cube just now. It's the same thing as well. So 1, 2, 3, 4, 5, 6. So face is 6. So vertex you have 8. Oh, sorry, not 8. Is it 8? Oh, yeah. So edges, you have 12. So that's why V plus F minus E. So 8 plus 6 minus 12. So it gives you 2. Okay. So which means that proves that this is a connected planar graph. Okay, so that's basically today's lesson. So I don't think it's very difficult, but you might need some time to get used with it, like how to draw and so on. Then try to use some time to attempt to the question. If let's say you have any question, then feel free to approach me. Okay, so yeah, that's it for today's lesson. Have a good day. Okay, bye.